In this video, we continue our discussion of sequences by talking about bounded sequences and monotonic sequences. This will be a relatively short video, and then we'll be getting on into series. And then remember that a series is when you add together the terms of a sequence. But first, we want to talk about what a bounded sequence is. Now, by bounded, we mean the value of the function, or in this case, a sequence, cannot go above or below a particular finite value. So by bounded, we mean that there's like a ceiling that it can't go above or a floor it can't go below. So bounded means between certain values, finite values. So this graph right here gives you an example of something that we would call bounded above. So there's a finite value right here, which we can call L or M or whatever you want to call it. And clearly, the terms of the sequence as n goes to infinity never go above L. So it's bounded above by L. Now, we can also talk about something that's bounded below. In this case, L, in fact, is the y value on the x-axis, which is 0. So it's bounded below by the x-axis in that the terms of the sequence are decreasing and getting lower and lower, but they never touch or go below the x-axis. So the x-axis, in a sense, is like a floor for the ceiling or a floor for the function, and it never goes below it. So this sequence is bounded below. Now, we can also have what we call a sequence that is bounded above and below. And in fact, the two that we saw up above are also bounded above and below. Now, this one is bounded above and below, but you can see that that does have some values at the beginning that are further away from where it is out towards the end. Now, remember that we have talked repeatedly about the fact that the first finite number of terms do not affect the convergence. So in fact, we can say that as long as there is a value out here, and it's bounded by that value, say L, and a value out here, and it's bounded by that value, say M, then we can call this a bounded sequence, even though the first terms may fit outside those boundaries. Again, it's the tail of the sequence that affects whether or not it converges, and we would call this bounded because it never goes above that line, y equal L, or below that line, y equal M. Now let's make this definition more formal. The definition is that the sequence is bounded above if there exists a real number m such that all the values of the sequence a sub n are less than or equal to m for all positive integers n, or n greater than some capital N. It's called an upper bound or eventually bounded. The sequence is bounded below if the value of m is such that m is less than or equal to the sequence values for all positive integers n, or we say it's eventually bounded below if it's true for some lowercase n greater than some uppercase n. We just call it bounded or a bounded sequence if it's bounded both above and bounded below. And if it's not bounded, then it's unbounded. So it's an either or situation. Either it's bounded or it's not bounded. If it's bounded, it could be bounded above, bounded below, or bounded both. This theorem is one of the most important ones when we're talking about sequences. And it basically says if the sequence A sub n converges, then it must be bounded. Because if it converges, it is getting closer and closer to some particular y value. And that must mean that we can put boundaries above and below that horizontal asymptote, where at some point, all the values of the sequence for thereon have to fit in between those boundaries. So if the sequence converges, in other words, the values of the sequence eventually approach some finite real value, then the sequence itself must be bounded. Likewise, if the sequence is not bounded, then the sequence A sub n must diverge. It cannot converge. Now, what do we mean by monotonic? So we've talked about bounded. What does monotonic mean? When we talk about monotonic, the root word, of course, is monotone, which is basically maintaining the same tone and not varying it. As you know, that's a really boring lecture, right? Where they talk in a voice and just drone on without any inflection. It's terrible, right? So monotonic, it's a function that doesn't both increase and decrease. In other words, it maintains one type of behavior. Either it's increasing for some value of the subscript lowercase n greater than some uppercase n, and it's always increasing from that point on, or it's always decreasing from that point on. In other words, once it picks a behavior, increase or decrease, it sticks with that behavior for some value of the subscript greater than some particular number. At some point, it always increases or it always decreases. That's what we mean by monotone. Now, in this case, monotone actually has a strict monotone meaning and a non-strict meaning. Monotone could be staying the same, or it could be always increasing, or it could be staying the same, or it could be decreasing. And we'll have to make this clear when we're talking about sequences. Again, we don't worry about the head of the sequence, the first finite number of terms. That doesn't affect convergence. We're only looking at the tail. Now, monotone and bounded have a great deal to do with the convergence of a sequence. So let's go ahead and make precise what we mean by monotone. We call the sequence increasing or monotone increasing if for all values of the subscript little n greater than some particular value, capital N, one of the three following conditions holds, and these are all equivalent. A sub n is less than or equal to a sub n plus 1. Now remember, when you make a list of the terms in your sequence, you may have a sub 0, a sub 1, a sub 2, and then at some point you have a sub n minus 1, then a sub n, and then a sub n plus 1. So to be increasing means the one that follows it is bigger than or equal to the one in front. The one in front is less than or equal to the next one in line. We call this non-strict monotone increasing because it could be equal to. So this is not strictly increasing, it's just increasing. If we take the or equal to off, we call it strictly increasing or strictly monotone increasing. You may or may not include the word monotone, but it's implied. Now, what's another way of showing that the sequence is increasing in values? You start basically with this relationship that the one in front is less than or equal to the next one. And you could subtract the a sub n plus 1 from both sides and show that a sub n minus a sub n plus 1 is less than or equal to 0. This comes directly from this inequality by subtracting the a sub n plus 1 term from both sides of the equation. So that makes sense. So these two are in fact equivalent to each other. What about the third? Well, the third is in fact equivalent to the first one, provided that a sub n and a sub n plus 1 are not 0. If that's the case, then a sub n divided by a sub n plus 1 has to be less than or equal to 1. And again, if we want strictly increasing, we would make it less than 1. And that just means that the ratio of the term in front divided by the term after has to be less than 1, and that means that it is strictly increasing. We call the sequence decreasing if for some value of the subscript lowercase n greater than some particular value of the subscript, maybe 42 or 437, one of the following three holds. And basically, these are equivalent to the three above, but with the inequality turned around. So the values would be going down in value if a sub n was greater than or equal to a sub n plus 1. We call it strictly decreasing or strictly monotone decreasing if a sub n is strictly greater than a sub n plus 1, no or equal to. And that would be the same as establishing that a sub n minus a sub n plus 1 is greater than or equal to 0, or that the ratio a sub n divided by a sub n plus 1 is greater than or equal to 1, right? So again, we have these three equivalent ways of showing that a particular sequence, the terms are either strictly increasing or strictly decreasing or decreasing. Now, note that when we include the or equal to, this could mean that the function is actually staying the same. So a constant function or a sequence that's a constant is by definition both increasing and decreasing, which is kind of a weird situation. But it's not strictly increasing or strictly decreasing because it's maintaining the same. So monotone basically means either staying the same or going up, or staying the same or going down. Strictly monotone means strictly going up or strictly going down, right? Now we want to make the definition precise for what we call a monotone sequence or monotonic. If the sequence A sub n is either an increasing sequence or a decreasing sequence, we call it monotonic or monotone. And this is the theorem that combines the idea of being bounded, trapped by some ceiling value and some floor value, with the idea of being monotone. And combining the two gives a condition for convergence of the sequence. So if we take a sequence and it's a bounded sequence, meaning there's some value it never goes above and some value it never goes below, and capital N is some integer such that all of the terms in the sequence are monotone once we get out there. So we're talking about the tail of the sequence, right? We're talking about the tail of it. Then A sub n has to converge. So bounded plus monotone means it has to converge. Well, why do you suppose that has to be? Why is this combination of bounded and monotone requiring that it converges? Why would we have that particular relationship? Let me draw a picture for you. I thought I might have one, but I don't see one. Here's an L and here's an M. So we've got this function here and this function here. They're basically horizontal asymptotes. And our sequence at some value of capital N is bounded in between L and M. So it may not be at first. So we're going to have some values out here for our sequence. And then it's coming in. And then it does this. Now, is that monotone? No, it's not. This is alternating. So it's bounded, but it's not monotone. So let's take the dots off and let's try one that is bounded and monotone at some point. So I'm going to take off these dots. If I can get them to erase without erasing my lines. Let's make it bounded and monotone decreasing. So we'll start with this one, which is not in the region. And then it comes below like this. But it's decreasing. But it's bounded, which means that at some point, it's going to approach some horizontal asymptote because we know it can't go below M, which must mean that eventually it approaches the value of M. So at some point right here, this would be our capital N value. From N on, it's bounded in between two different horizontal asymptotes, but it's maintaining the same behavior, decreasing. And that means that it must converge because it keeps going down. It's got to eventually approach M. What would happen if it were increasing? If it were increasing, we would have a similar behavior, but in fact, it would be approaching L. So in this case, we would have something coming up here like this. And then from N, all the values fit between L and M, but it's constantly increasing, so still going up, but it can never get above L. That must mean that it's approaching the value of L, so we would say that the sequence converges. So this idea of bounded plus monotonic gives us convergence. Now, we are mostly concerned with sequences that converge to finite real numbers, so we tend to ignore the unbounded, strictly increasing sequences. If they're not bounded, they're going up to infinity forever. Likewise, if it's not bounded and strictly decreasing, then it goes to negative infinity. So they're also little interests. So we would have a negative infinity there. Sorry, I lost my negative. So mostly what we're looking for then are sequences that are bounded and monotonic. And in fact, most of the time, what we're looking for are strictly decreasing sequences that are bounded sequences of positive values which approach 0 as x goes to infinity. Now, why do we want them to approach 0? Remember that what we're talking about here are sequences, but the eventual point to this whole discussion is to get to series. Series take all the terms in a sequence and add them together. Well, if it's approaching the value of L, then that may mean that I've got some value here, and a value here, and a value here, and a value here. But way out there somewhere, it's about L, close to L, practically L. And if the sequence goes forever, if L is not 0, then the sum is definitely going to blow up and go to infinity. So the only chance we have for the sum of a sequence to add up to a finite number is if the limit of the sequence, the L value, is practically 0. So if all of these instead become practically 0, then it's possible, not for sure, but it's possible that it might add up to a finite number. And this is what we want to do when we study series. So we are primarily interested in strictly decreasing bounded sequences where the limit of the sequence is going to 0 as the subscript goes to infinity. Now, we want to show, because we're interested in that type, we want to know, how do we show that a sequence is decreasing? So when we look at this, there are 3 basic ways that I will accept from my students to show that a sequence is decreasing. These all show the same thing. The first 2 are equivalent to one another, but the third one, of course, is not. The first 2 come from the inequality that we saw up above, and this is strictly decreasing, so we do not have an or equal to. So this would be a sub n plus 1 minus a sub n is less than 0, which comes from a sub n plus 1 is less than a sub n. This means the one after is smaller than the one in front. The values are going down. Likewise, we could take this particular relationship and we could divide both sides by a sub n, and we would get a sub n plus 1 over a sub n is strictly less than 1. So if I can show, using the formula for a sub n with n plus 1 plugged in one time and n plugged in the other, that one of these 2 relationships hold, then I proved, using the formula, that it is a strictly decreasing sequence. Now, the next one that we can use to show it's strictly decreasing is to use the first derivative test. So we would use the formula for a sub n by representing it as some function of n and take the derivative of it. And if we can prove, using the formula, that the first derivative has to be negative, either for all values of lowercase n or for some value of n greater than capital N, in other words, the tail of it is always decreasing, then again, we've shown that the sequence is decreasing. Showing that a sequence is decreasing for a pair of successive terms, a specific pair, is meaningless. You have to either use the formula with a sub n plus 1 and a sub n, or you have to use the derivative test. You could, in fact, show that successive pairs of terms are decreasing for a billion or a trillion or a googolplex of successive terms. It's meaningless. Infinity is so much vaster than either of those numbers. It's a drop in the bucket. It doesn't mean anything. We haven't proved it for the tail by proving it for a finite number of terms at the beginning. You must use the formula for a sub n plus 1 and a sub n, and either this inequality or this one, or you must take the derivative of the formula of a sub n using the first derivative test. Now let's take a look at example 11, and we want to show how to prove that this is a decreasing sequence using all 3 of our methods. So let's go ahead and rewrite our 3 methods one at a time. So our first method was a sub n plus 1 minus a sub n is less than 0. Now, how can I prove this using the formula for a sub n and a sub n plus 1. Well, I come over here to the definition of the sequence, which is 1 over n squared, and I rewrite that using the formula. So I replace the n with n plus 1 quantity squared, and then a sub n is given to be 1 over n squared. And the question is that really less than 0? I don't know. That's what I'm trying to prove. So in order to do this, what might we do first? Well, the first thing I would do would be to get the fractions on opposite sides of the inequality. So I would move the 1 over n squared to the right side by adding it to both sides of the equation. So I'm going to move this to the right side of this inequality, and that would give me the relationship that 1 over quantity n plus 1 squared is less than 1 over n squared. Now keep in mind that n started with 1. So n squared is strictly positive and n plus 1 is strictly positive. So I know that 1 over n plus 1 quantity squared and 1 over n squared, they're both positive. Well, they would be positive anyway, right? They're squared. So because they're positive, I can multiply both sides by them. That means that I can get rid of the fractions by multiplying both sides by the denominator. So I can multiply this side by n squared, n plus 1 quantity squared, and I can multiply this side by n squared, n plus 1 quantity squared. And that would result in the following equation, that n squared is on the left end of the symbol, the small end, less than n plus 1 quantity squared. But of course, I'm trying to establish that this is true. I'm trying to prove that it's true. If I can prove it's true, then I've proved that it is a strictly decreasing sequence. So I have n squared here, and I have n plus 1 quantity squared here. Now, there's more than one way to go from this point. You can take the square root of both sides, but then we usually have to worry about plus or minus, although we know that both n plus 1 and n are positive, so we could just take the primary root. But another way of doing it that doesn't involve that kind of ambiguity, would just be to multiply out the right side. So I have n squared, is that really less than? Well, if I multiply it out, I get n squared plus 2n plus 1. Well, then I can subtract n squared from both sides of the equation. And this says 0 is less than 2n plus 1. But we know that the lowest subscript value is 1. So this has to be true. 2 times 1 plus 1 is definitely positive. No matter what n is, this right side is going to be positive, and that's always going to be greater than 0. So this is always true. Therefore, we've shown that it is strictly decreasing. So the whole point was to prove that the inequality was true, and that was the first example. Now we want to go back to the beginning, and we want to prove it using the second method, which is an plus 1 over a sub n less than 1. So this would be the second method. What did I say it was again? A sub n plus 1 over a sub n. We want to show that's strictly less than 1. Now remember that our a sub n is equal to 1 over n squared for n equal 1 to infinity. That was the sequence that we were working with. So the next thing that we want to do here is we want to take this and we want to use the formulas for a sub n plus 1 and a sub n just like we did up above. So the formula that we have here is going to be 1 over quantity n plus 1 squared, that's a sub n plus 1, and a sub n is 1 over n squared, and I'm trying to prove that it's less than 1. I don't know that it's less than 1, I'm trying to prove that. But this is, of course, a complex fraction. It has 4 parts, the numerator, denominator, the numerator, the denominator, the denominator. Basically, the numerator, the 2 n's, and the denominator, the 2 d's, both belong in the numerator. And the parts in the middle both belong in the denominator. So we can rewrite this one in an equivalent form which would basically give rise to the following expression, that n squared over n plus 1 quantity squared replaces that complex fraction. And we want to prove it's less than 1. Well, then I've got something squared over something squared, so I could pull the square off both, and that would give rise to the following expression, that n over n plus 1 squared is that less than 1. Now, I know that n is strictly positive and n plus 1 is strictly positive, so I can take the square root of both sides. And if I take the square root of both sides, then I know that n over n plus 1 is going to be what I have on the left. And on the right, the square root of 1, of course, is 1. So the question is n over n plus 1 less than 1? Well, you know it's less than 1. One of the things that you can do to prove it, of course, is to multiply both sides by n plus 1. It's strictly positive. And when you multiply both sides by n plus 1, it does not reverse the inequality because it's strictly positive. And this gives rise to the statement n is less than n plus 1, which we know to be true. It is true that n is less than n plus 1. You could subtract the n's, one from each side, and that would tell you that 0 is less than 1, which is always true. So again, we prove that it's strictly decreasing. Now, these methods always work. They're perfectly valid. They're not my favorite. My favorite is probably the third method. So let's take a look at the third method of showing that a particular sequence is strictly decreasing. So again, we're going to start with our expression for the sequence, which is 1 over n squared from n equal 1 to infinity. Now, in this case, I said that we rewrite it as some function of n, which is just 1 over n squared, and I take the derivative of it. Well, if I'm going to take the derivative of it, I take the derivative with respect to n, since that's the domain variable, right? N is my subscript, so it's my domain variable. So I'm taking the derivative with respect to n, and it may be helpful then if you think of this as n to the negative 2 using the power form instead of 1 over n squared. And then we can just apply the power rule, which of course gives us negative 2 n to the negative 3. Remember, the negative 3 power just drops it back into the denominator, and we end up with negative 2 divided by n cubed. Now, how does that help? What does that prove? Well, I know that n is strictly positive because it starts at 1. And since n starts at 1, n has to be strictly positive, so n cubed is positive. And if the denominator is always positive, but the numerator is always negative 2, then this is always going to be negative for all values of n. So this is going to be less than 0 for all values of n. And we write that using an upside down print A, and that stands for the words for all. So this means that this is less than 0 for all n. And this proves, using the first derivative test, that it is decreasing. Remember, the first derivative test tells you if something is decreasing or increasing. If the first derivative is positive, it's increasing. If the first derivative is negative, it's decreasing. And in this case, it's decreasing no matter what the value of n is. This ends our discussion of what we have to discuss about monotone and bounded. So we've seen that monotone describes something that is either staying the same or increasing, staying the same or decreasing. Bounded means it fits in between two horizontal asymptotes, has a ceiling function and a floor function. And at some point, all the values of the sequence are between. And we've seen that the combination of bounded plus monotone guarantees that the sequence converges. And then the last thing we looked at was, how do we determine if it's strictly decreasing? Because again, the sequences we're most concerned with when we get to series are the ones that are decreasing, strictly decreasing, and approaching 0. Because we're going to be adding up all these terms, we need the values to eventually be practically 0 so that we have even a chance, just a chance, that they'll add up to a finite number. And that's what we're going to see in the next video, when we start our study of series.